Hey class, today I will be teaching you about fitness landscape analysis and why you should care about it. First, we will discuss some background on fitness landscapes. Then we will answer the question, what is a fitness landscape, and provide some definitions. Then we will discuss some specific fitness landscape analysis metrics, density of states, local optima, fitness distance correlation, FDC for short, basins of attraction, neutral networks, and autocorrelation. Lastly, we will discuss why we should care about fitness landscape analysis. Fitness landscape analysis originated from evolutionary biology as a way to analyze how different gene combinations contribute to the fitness of an organism. Now, fitness landscape analysis is often applied to optimization problems in computer science as part of a subfield called evolutionary computation. So, what is a fitness landscape? Broadly speaking, a fitness landscape consists of a search space, a distance metric, and a fitness function. Let's go over each of these in more detail. Let's call our search space Big X. A little x belonging to Big X is called a solution candidate. Oftentimes, for optimization problems, the search space is a finite combinatorial search space. Finite meaning there is an upper limit to the number of solution candidates in the search space, and combinatorial meaning each solution candidate is some combination or permutation of items from a set. For example, an RNA strand is made of nucleotides, an 8-byte chessboard is made of chess pieces, including an empty space, and a Scrabble word is made of Scrabble letters. For the rest of this video, we will be using 5-letter Scrabble words for our example fitness landscape. In addition to a search space, a fitness landscape also needs a distance metric. A distance metric has the following properties. It is non-negative, meaning the distance between any two solution candidates is at least 0, and the distance between two solution candidates is 0 if and only if the two solution candidates are identical. The distance metric must be symmetric, meaning that the distance is the same no matter what order the arguments are in. Lastly, the distance metric must satisfy the triangle inequality, meaning that the distance between x1 and x2 plus the distance between x2 and x3 must be at least the distance between x1 and x3. One popular distance metric is Hamming distance, which is the number of substitutions required to get from one string to another string. In this example, the Hamming distance between the words watch and water is 2. We define the neighborhood of a solution candidate x as the set of all solution candidates that have a distance of 1 with x. I want to briefly note that some definitions of fitness landscapes skip directly to a neighborhood definition instead of using distance metrics, but I chose to provide this definition because it is highly applicable to finite combinatorial search spaces, which, as I said earlier, is common for optimization problems. The fitness function assigns a real value fitness score to the solution candidate. So in our Scrabble example, the fitness function of a Scrabble word would be the Scrabble score. We could say that it is 0 for invalid Scrabble words, and the sum of the letter scores for valid Scrabble words. Now that we've defined a fitness landscape, the next question is, what is a fitness landscape analysis? I'm going to describe fitness landscape analysis by first making an analogy to chemistry. Say you're a chemist working in a lab, and you come across a mysterious substance. You've never seen anything like it before, and you want to do your best to figure out what it is. To do this, you might ask questions like, what does it look like? What does it smell like? What is its melting point? Does it float? How dense is it? And if you're really brave, you might want to know what it tastes like. The key idea here is, because we don't know anything about the substance, it's not enough to only use one of these measurements to figure out what it is. We need many tests in order to have a better idea of what the mysterious substance is. Fitness landscape analysis is very similar, but instead of a mysterious substance, we have a mysterious fitness landscape, which we don't know much about. And instead of doing physical tests to find out what a substance is, we use fitness landscape analysis metrics in order to get more information about the fitness landscape. Just like with a mysterious substance, we need many metrics in order to get a good picture of the fitness landscape. Even then, we will never be able to understand it in its entirety. In this video, we will cover popular metrics such as density of states, fitness distance correlation, local optima, basins of attraction, neutral networks, and autocorrelation. But I want to emphasize that there are many more metrics out there as well. A density of states analysis answers the question, how many solution candidates are at each fitness value? Plotting the density of states of a fitness landscape might result in a visualization that looks like one of these 3 histograms. So why care about density of states? We care about density of states because density of states can tell us how difficult a problem is for random search. For example, in the leftmost histogram, most solution candidates have low fitness, so this problem will be very difficult for random search. The middle histogram has an approximately uniform distribution, so this problem would be easier than the previous one for random search. In the rightmost histogram, most solution candidates have high fitness, so this problem will be easy for random search. Next, let's talk about fitness distance correlation, commonly abbreviated as FDC. FDC is the Pearson correlation coefficient between fitness and distance to the nearest global optimum, with global optimum meaning the fittest solution candidate. It can be found using this equation. If you're looking into this stuff on your own, reading papers about fitness landscape analysis, you might run into equations for FDC that look a little different. This is just because the formula for Pearson's correlation coefficient can be written in a lot of different ways. Unfortunately, many authors don't state that FDC is just a specific application of a pre-existing statistical coefficient, which can be very confusing. But if you're ever confused, just remember, FDC is Pearson's correlation coefficient between fitness and distance to the nearest global optimum. So why care about FDC? We care about FDC because FDC can be a measure of problem difficulty for genetic algorithms. Some authors don't mention the genetic algorithms bit, so keep that in mind when you are doing your own reading. FDC can divide problems into 3 categories of difficulty, again, for genetic algorithms. An FDC of less than or equal to negative 0.15 is straightforward because solution candidates increase in fitness as they get closer to a global optimum. An FDC between negative 0.15 and 0.15 is difficult because there is weak to no correlation between fitness and distance to a global optimum. Lastly, an FDC of greater than or equal to 0.15 is misleading because solution candidates decrease in fitness as they approach a global optimum. There are 2 types of local optima. For a maximization problem, such as maximizing fitness, a local optimum is a local maximum. For a minimization problem, such as minimizing loss, a local optimum is a local minimum. For the rest of this video, I will be referring to a maximization problem. So if you're interested in a minimization problem, you can reverse the signs. A solution candidate is a local optimum if it is the fittest in its neighborhood. For example, the Scrabble word Jiffy is a local optimum because it is fitter than all the other 5-letter Scrabble words that are 1 letter away. Why care about local optima? Local optima can tell us about the global ruggedness of a fitness landscape. Global meaning we are taking a zoomed out look at the fitness landscape. For example, a fitness landscape with more local optima means that it is more globally rugged. Furthermore, the FDC of local optima can tell us if there's a progression of fitness towards a global optimum. So for example, in this graph of fitness versus position, we can see that there's no progression of local optima fitness towards the global optimum. But in this graph of fitness versus position, we see that the fitness of local optima increases as they approach the global optimum. We can examine not only local optima, but also the areas around local optima, which are called basins of attraction. To understand basins of attraction, we must first define some terms. An upward path is a sequence of solution candidates with the following properties. Each solution candidate in the sequence is neighbors with both its predecessor and its successor, and the fitnesses in the sequence are non-decreasing. You could intuitively think of an upward path as hopping from neighborhood to adjacent neighborhood, while fitnesses increase or stay the same. Then a weak basin of attraction of a local optimum is the set of all solution candidates with an upward path to that optimum, and a strong basin of attraction of a local optimum as the set of all solution candidates with an upward path only to that optimum. In other words, a strong basin of attraction of a local optimum is everything in the weak basin of attraction that is not in any other weak basin of attraction. Looking at a previous example, we see that Niffy, Biffy, and Miffy each have an upward path to Jiffy, so they are in Jiffy's weak basin of attraction. If we go 1 level out, we can see that Nifty, Buffy, and Miffs also have an upward path to Jiffy, so they are also in Jiffy's weak basin of attraction. I would guess that they are also in Jiffy's strong basin of attraction, but I haven't run the code to see if that's actually true, so I'll leave that as an exercise to the viewer. Why care about basins of attraction? Basins of attraction can tell us about problem difficulty for local search methods. This is because a local optimum with a larger basin of attraction is more likely to be found via local search. So for example, if a fitness landscape has a local optimum with low fitness but a large basin of attraction, and a global optimum with high fitness but a small basin of attraction, that would be a difficult problem for local search methods, because they would tend to get stuck in the worst local optimum. While basins of attraction lead to a local optimum, a neutral network is a set of connected solution candidates with equal fitness, and can be thought of intuitively as a plateau of fitness. Let's look at a previous example. You'll notice that Biffy and Buffy are connected solution candidates with the same score, so they form a neutral network. Here is a much larger neutral network. I might have missed some words, so let me know in the comments below if there's any word I missed. So why care about neutral networks? We care about neutral networks because they give us access to a lot of different solution candidates while maintaining the same fitness level, allowing us to explore the space without decreasing in fitness. Lastly, I want to talk about autocorrelation. The autocorrelation function for a lag I is the Pearson correlation coefficient between a random walk on the fitness landscape and the same walk with time delay I. The autocorrelation function has the following formula. Again, you might see some different formulas for the autocorrelation function, but just remember that it is a Pearson correlation coefficient. Related to autocorrelation is correlation length, which is the expected distance between points before they become uncorrelated. Correlation length can be found using this equation. So why care about autocorrelation and correlation length? Autocorrelation and correlation length can tell us about the local ruggedness of a fitness landscape. Whereas local optima looked at a zoomed out view of the fitness landscape's ruggedness, autocorrelation and correlation length looked at the zoomed in view. For example, an autocorrelation function that decays slowly, like this, will have a large correlation length, indicating a locally smooth fitness landscape. On the other hand, an autocorrelation function that decays faster will have a small correlation length, indicating a locally rugged fitness landscape. So, I've told you about why you should care about each metric we've discussed in this video, but now I want to talk about why we should care about fitness landscape analysis as a whole concept. When we have a problem, it's really tempting to jump straight to a solution. What fitness landscape analysis does is that it lets us get a better understanding of the problem, which we can then use to craft a better solution. Also, I personally think it's inherently interesting, even if we don't end up creating a solution. Let's summarize what we've learned today. We learned that a fitness landscape consists of a search space, a distance function, and a fitness function, and fitness landscape analysis is one method we can use to understand problem difficulty. One metric we looked at is density of states, which answers the question of how many solution candidates there are at each fitness value. Fitness distance correlation, or FDC for short, is the Pearson correlation coefficient between fitness and distance to the global optimum. A local optimum is a solution candidate that is fitter than its neighbors. A weak basin of attraction of a local optimum is a set of solution candidates with an upward path to that local optimum, with an upward path being a sequence of solution candidates where each solution candidate is neighbors with its predecessor and successor, and the sequence is non-decreasing in fitness. A strong basin of attraction of a local optimum is the set of all solution candidates with an upward path only to that local optimum. A neutral network is a connected area of equal fitness. The autocorrelation function is the Pearson correlation coefficient between a random walk and the same random walk with a time delay, and the correlation length is the expected distance between points before they become uncorrelated. We should also remember that there are many other fitness landscape metrics, and these are just a few. We learned that we should care about fitness landscape analysis because it can give insight into the problem itself, for example, by indicating problem difficulty for different search methods. Thank you so much for watching, and please feel free to comment any questions you have about the video, topics you would like me to cover next, or any feedback for how we can improve my videos. As always, this is your CS Professor of Fun.